Okay, perfect. All right, so today we're going to cover nebular theory, and it's something that people should start with when talking about the environmental science because that's how our Earth formed, right? And in order for us to understand how we utilize the science that we have, we need to understand how did we get here, right? Kind of address the patterns that we have within our solar system to understand why is Earth different than any other planet, okay? Because we know that people have been questioning, the existence of our planet and the pattern in sky appearance for as long as there have been people, okay? People have been using stars and constellations that they would see patterns in appearance for things like planting and harvest, right? They didn't have an iPhone 11 in their back pocket to see that it's March 15th and they should start thinking about planting their crops. They would find constellations of stars that would appear around that time, and at that point decide, okay, it's time to plant. Same thing when it came to harvest time, right? You don't want to harvest your plants or your crops too early or wait too long and then have your first frost killing your crops. So they would collect data for a really long time without maybe necessarily knowing that they're collecting data, right? They may have, seen the patterns of different constellations appearing and say, I remember this pattern appearing in the night sky at sunset. We should think about planting. We have data from early civilizations. I mean, Mayans were amazing in keeping track of stars, and they were really fascinated with Venus. But we have all of their data kind of, documenting major events in astronomy, which allowed people then to make predictions and figure out what's happening and what happened in the past. Once people started getting better and better in math and science, they were able to take those pieces of data and start analyzing it and start putting together models. Now, you guys, I'm sure, are aware of the fact that the first models of the solar system were not very good, right? They were pretty wacky. And they had to go to a very extensive craziness to try to explain the patterns that they would see in the night sky. Because oftentimes back then, science was limited by religion, right? People needed to formulate a model of a solar system that allowed the information that those, introduced in the Bible to be involved in that model of a solar system. Now we know that that's not how science works, right? You can't just pick and choose what data you're going to use and what pieces of information, fulfill your agenda or your bias or whatever your end goal is. So now we know that that's not how it works. So after scientists were able to plot that data, they were able to come up with a solar system model. And now we know that there are many different properties within our solar system that need to be addressed if we are going to come up with a path of formation of a solar system. Because this process is true not only for our solar system, but for all solar systems that we see out in space. So we know that each of our 8 planets are fairly isolated from each other, right? They are pretty far away from each other, relatively speaking, okay? Because everything in space is relative. If you think about the distance between the Earth and the Moon, you can say from our perspective, Moon is pretty far away, right? But if you think about the distance between the Earth and the Moon on a scale of our solar system, you're going to be like, well, it's really not that far, right? If you think about the distance between the Earth and the Moon on a scale of a Milky Way galaxy, heck, we're next door neighbors, right? We're pretty much on top of each other. So everything is relative. But for each of our planet to be isolated in space and be kind of far away from each other, that had to be addressed. We also know that the orbits of our planets are not perfect circles. Early astronomers thought they were, but now we know that they're not. Okay. We also know that all planets orbit on the same plane of motion. If you could imagine taking a CD and putting a drawing bunch of dots on the surface of that CD and then spinning that CD on your finger, well, you would notice that all those dots that you drew travel in the same plane of motion, right? In addition, they also travel in the same direction. It's not like some of the dots are going to say, wait, I want to go the other way, and then magically start going the other direction. So that's something that needed to be addressed. We also know that our solar system is highly differentiated, meaning that our planets are very different from each other. Even though we have our terrestrial planets and our gas giants, every single planet is different from the rest of them. Okay. We know that we have an asteroid belt between the rocky and the ice planets, or the gas planets, right? Why is it there? Why is it a good indicator of the age of our solar system? The Kuiper Belt is a collection of icy bodies that lie beyond the orbit of Neptune. That's where our comets are coming from. Okay? And then the Oort cloud is way beyond that, and it's pretty much our boundary of our solar system and deep space. So here we have a bunch of scientific terms that you should be familiar with. I am not going to ask you to recite them to me. The one thing that I do want to focus on is the last one, which is a theory. A theory is not something that you will oftentimes hear from people that are not very good or very familiar with science. They're going to say, well, theory is just like an educated guess, or, it's something that they made up. It's just a theory. Who knows? That is as far from the truth in science as one can get. Because theory is a very thoroughly researched process that incorporates a lot of scientific laws that will help us explain what we're seeing, why do things act the way they do, and it will allow us to make predictions. Okay? When we think about the theory of plate tectonics, I'm using that because I'm assuming you guys are familiar with that. Based on previous observations, we can make predictions as to which way the plates are going to move. Right? We have equipment that measures the movement of plates pretty much on a daily basis. And it is extremely precise. Think about your cell phone that you carry in your pocket. When you pull up your Maps app, you see that little blue dot showing your exact location, right? If you stand on your front yard and look at your little location on your cell phone, it is going to be pretty precise. Like if you zoom in on the map, it's pretty close. And then if you move and you walk to the backyard, oftentimes you will see that little dot walking with you, right? That's just your cell phone, right? That's that precise. So now think about scientists that focus on the plate movements, how precise their equipment is going to be to measure those locations, right? Based on our previous data, we can make predictions in terms of where will the plates move next week, a year from now, 20 years from now, 1,000,000 years from now. We actually know that in 150 million years, we're going to have another supercontinent. They named it Amasia. because scientists can look at the pattern of movement and say, in 150 million years, this is where the plates are going to be. Okay. So a theory that was put together for the formation of our solar system had to address some of those main points. Like, why do we have planets that move in a fairly predictable way? Why do we have two different types of planets? And why are they where they are at? Why do we have asteroids and comets? Why is the appearance of Halley's Comet every 76 years predictable? Chances are that people that have seen a Halley's Comet once in their lifetime will not see it again. Right? If you think about it, that's pretty much once in a lifetime opportunity. And of course, a good theory needs to allow us to answer the questions on some exceptions to the rules. For example, why is Mercury's orbit not perfectly aligned with everybody else? It's not traveling on the perfectly same plane. And that's where they came up with the nebular theory. Okay, a nebula is a big interstellar cloud of dust particles and gas. And if you look closely in the night sky, you can actually see the Orion Nebula within the Orion constellation. It's actually visible in winter months. It's fairly easy to identify. And we can observe those nebulae in the night sky. We have photographs of hundreds of them. And within these nebulae, we can actually see the solar systems forming and at different stages of formation. So then scientists can piece it together and say, okay, this is the process, right? It's the step-by-step what happens. Because I don't think anybody has, 200 million years to sit around and watch a new solar system form. So what happens is there's this nebula that's hanging around in space and it's slowly rotating. I mean, there's barely any movement in there. And then there's some sort of event that starts the process. Oftentimes, that event is a nearby star that goes through the process known as supernova. And that's when you have the massive star explode. No, our sun is never going to explode. It's not big enough. In order for a star to go through a supernova, it needs to be about 3.5 times the mass of the sun. Okay? So our sun will never blow up. You will not wake up one day to a dark morning. And even if we did, you wouldn't wake up in the morning. So anyways, we have a supernova that sends out this pulse of energy into space. Right? And that begins the movement of material within the nebula. Well, now that you have movement of the dust and gas particles within the nebula, well, physics is going to take over. Right? We have Newton's laws that apply in the entire universe. A body in motion or an object in motion will stay in motion. So whatever particle has gotten the push, it will continue to move unless there's another force acting upon it. Well, gravity is going to take over, right? And now you're going to have particles that accelerate towards each other. In particular, smaller, less massive particles are going to accelerate towards more massive particles, right? You have mass. You exert your own gravitational pull. You literally pull on everything in the universe. Now, your gravitational pull is not very much because you're not very massive, right? But you have your own gravitational pull. So as those particles accelerate towards each other, they lump together, increasing their mass, therefore increasing their gravitational pull. right? At that point, this cloud that's slowly rotating will have the more massive materials come closer to the center, therefore making the cloud spin faster. Just as this ice skater is spinning faster when she pulls her arms closer to her chest. Right? We've all seen this before. And they can change their spin by either extending their arms or pulling them together. And they can keep doing it over and over again. Right? And they can slow down or speed up. Well, in a nebula, once those particles are closer to the center, they're going to spin faster. And the nebula is going to spin faster. That's because of conservation of angular momentum. And when you talk about this topic in physics, you're going to be like, wait, I remember that. We talked about this. So this is pretty much what it looks like, where you have this nebula beginning to spin, right? As the material will concentrate towards the center, it will concentrate the mass towards the center, therefore making the cloud spin faster. So the cloud spins because it's part of a spinning galaxy, right? Which there's a lot of angular momentum available. As the nebula collapses upon itself, you're going to have all this material kind of condensing inside or in the center of it. It is going to have a lot of collisions, and material is going to grow in size because of its gravitational pull and pulling on additional material. So eventually that spinning nebula, that spinning cloud, is going to take shape of a disk or a pancake. Okay? And then the entire disk is spinning in the same direction. Eventually what's going to happen, you're going to have hydrogen atoms that find different hydrogen atoms and they smash into each other in very, very simple terms. Okay? As they smash into each other, they go through the process of nuclear fusion, meaning that their nuclei are actually going to fuse together. During that fusion, you have two things given off. You have heat given off as a result of that nuclear fusion reaction, and you release a photon. A photon is a particle of light. Now, if you think about it, when you have heat given off and light being emitted, now you have a protostar. Okay, so now you have this star that's formed in the center of your spinning disk. Eventually, because of the process known as accretion, you are going to have planetesimals grow larger and larger in size. They actually go in and they sweep their orbital path, right? Because as they travel in space, they will attract and they will sweep up everything that's in their path, therefore growing in size, therefore sweeping more things that are in their path, eventually clearing of the path. So eventually your planetesimals are going to accrete large enough and eventually turn into planets. Okay? So having this nebular theory will allow us to answer those questions and kind of address the points of the different types of motions in our solar system, right? We have the sun in the center because it formed because of nuclear fusion, right? We have the movement of planets. The heavier material stayed closer to the sun. Therefore, we formed our rocky planets closer to the sun. The gas and ice was sent out to an outer part of the solar system, and that's where eventually the gas giants were formed. Okay. So again, this is pretty much what I just said. The farther away you are from the sun, the colder the environments are going to be. So your gas giants and your icy particles could last there, right? If you put a gas giant near the sun, well, the solar wind is just going to blow it away, right? Because it needs to be cold for it to happen. So this is where you have the terrestrial planets being built closer to the center because of the process of accretion. And that's a term that you will need to be familiar with. The gas giants were formed, again, by gas accretion farther away from the sun. Accretion is pretty much the process of accumulation of material to grow larger and larger planets. The gas giants almost, if you could think about it, almost created their own nebula. And that's where they spun into the planets that we have now. And then they have all those multiple moons orbiting around them. The solar wind is what pretty much carried the gases out into the outer parts of our solar system. If we did not have a magnetic field within our planet would not be able to hold on to its atmosphere because the solar wind would literally blow it away. But we know that solar wind happens, and we know that we have a magnetic field protecting us from that because we see northern lights. That's pretty much what northern lights are. It's the plasma that's coming from the sun through solar wind, and it's interacting with our magnetic field. The asteroids are located between the terrestrial planets and the gas giants. It's believed that asteroids, where the asteroids are, there should have been another planet. But because of the massive gravitational pull of Jupiter, that accretion never happened. Because Jupiter prevented the material from accumulating with other asteroids. Okay. And this is a image showing you where the asteroid belt is, which is the first ring of those little dots, right? The blue orbit is the orbit of Neptune. And then beyond that, we have our Kuiper belt. Right here. And then we have the Oort cloud beyond that. Okay, so this is where I'm going to stop for today. And then we are going to resume this next week.